Now that we have a stiffness matrix, we can explore several stress and strain paths. One of those is the uniaxial strain loading stress path. In the uniaxial strain loading, what we have is just deformation on one direction. In this example, we have a stress which is applied in direction 3, which produces a contraction in direction 3. We may think of this stress as an action, and as a result, we're going to have a response or a reaction which is going to be a horizontal stress, because in this case we're going to impose that there is no deformation to the sides. This is the opposite of what you would have, for example, in unconfined or constant stress conditions. In those conditions, when you apply stress, the solid will expand to the sides due to the Poisson effect, as long as the Poisson ratio is higher than 0. But in this case, it can't. And as a result, stresses develop as a function of the Poisson ratio. All right, so the mathematical conditions or the strain conditions that we're going to see then are the deformation, linear deformation in direction 1 and 2 are equal to 0. We do have the deformation in direction 3, and also that the shear strains are equal to 0. All right, so let's solve this problem to see what modulus characterizes this type of deformation, and also how we can predict a horizontal stress. Before we do that, let me tell you that this condition applies very nicely for many cases in the subsurface. For example, in places that are tectonically passive, when you have sedimentation over time and more sediments pile on top of each other, if there is no tectonic strain either extending these sediments or compressing them in horizontal direction, then you would expect also to have this one-dimensional strain condition in which there is just compaction in one direction. So as long as that happens, then you can apply the assumption that we are doing right now. Okay, so coming back to here, then we're going to apply these conditions on our relationship between stress and strain in order to calculate the relationship between those. And here, epsilon 1 is going to be equal to 0, epsilon 2 as well. The shear strains are equal to 0. And the first thing I'm going to do here is to calculate what is going to be the relationship between the vertical stress and the vertical strain. In order to do that, what I have to do is to multiply the third row times the vector column of strains. And as we can see, the only element that's going to survive is, from all of that dot product, is going to be the product of this times that times this. And then this is going to be like this. This is the part of the stiffness matrix. It is actually the component C33, and this is going to be multiplied times the vertical strain. All right, so just by doing that simple multiplication, we have arrived to a very important equation that defines something which is called the constraint modulus, and it goes by the letter M. Let me write a little bit better that M. It goes by letter M, and it's called constraint modulus. And notice that it relates a vertical stress and a vertical strain. If you remember from the definition of the Young modulus, we also use a vertical stress and a vertical strain. But in the case of the Young modulus, we have a boundary condition in which the solid could expand to the sides. And this is not the case. In this case, the solid cannot expand. So if you were to compare the Young modulus and the Young modulus, what would you say? Which one is bigger, the constraint modulus of the Young modulus? Well, in order to solve that, let's try to look at this example. As long as the Poisson ratio is higher than 0, you could imagine that if you were to compress this solid and achieve a given strain, let's say 1%, it's going to be harder to do that if you have the sides which are not able to expand to the sides or to relax that stress I am applying, than if I had that boundary condition holding the solid to the sides. As a result, as long as the Young modulus, the Poisson ratio is larger than 0, then the constraint modulus is going to be larger than the Young modulus. The constraint modulus, it's very important. It's a very important property and reflects more accurately the deformation of a three-dimensional solid under these boundary conditions, and as we saw later, also under conditions, for example, of sedimentation, natural sedimentation conditions and compaction, and also we're going to see later under conditions of, for example, depletion of a reservoir. So this is a very important modulus. And also this is called, as well, has a name of the holometric modulus. This is the name which is given in solid mechanics. I have to say too that solid mechanics has been very successful lately in order to describe the evolution of young unconsolidated sediments over geological time. So it's becoming more and more popular in structural geology. And it is also the P wave modulus, because P waves move with causing a deformation similar to the one that we see over here. We'll come back to this later on. All right, so let's see now how we can use the matrix, the stiffness matrix, and our boundary conditions in order to predict horizontal stress. Let's take the horizontal stress sigma 11. In order to calculate sigma 11, I need to multiply the first row times the column vector, and notice that now the only element that's going to survive from this dot product is going to be this one times that times this. And let me write that. This is going to be the Poisson ratio times the common factor in the stiffness matrix times epsilon 33. But notice that we can get epsilon 33 from the previous equation. So this is going to be what I had before, times epsilon 33, and now epsilon 33, if I solve for epsilon 33 in this equation and I put it in this one, is going to be the ratio of these two quantities, which I'm writing right now, minus Poisson ratio times epsilon, times sigma 33. That is epsilon 33. And from here, we can see right away that we can cancel out some terms like this one, that one, even the Young modulus. The Young modulus cancels out, and as a result, sigma 11 is going to be equal to the Poisson ratio divided 1 minus the Poisson ratio times sigma 3. So what this equation tells me is that the horizontal stress sigma 11 is a direct function of the effective vertical stress sigma 33 through this coefficient, which goes by the name of lateral effective stress coefficient, and for example in the solid mechanics community goes by the name of K naught. Let me write that K again so it's clear. Alright, so let's see now what is ratio, what is the value for typical values of the Poisson ratio. And for that I have a schematic over here that I have already drawn, and here we can see that depending on the value of the Poisson ratio, the effective lateral stress coefficient is going to vary. Poisson ratio goes from 0 to close to 0.5 for most solids, and is equal to 0.5, for example, for a fluid. For a typical Poisson ratio of 0.25, this is going to be 0.25 divided 1 minus 0.25, and that's going to be equal to 1 over 3, or 0.333 periodic. So for a typical then Poisson ratio, this is telling me that the effective horizontal stress is going to be 1/3 of the effective vertical stress. And I hope that you can see the implications of this. And you could rephrase this by saying that the solid, when it's compressed with a given stress, or if we think in terms of overburden, when it tries to expand to the sides, it's not pushing with all the weight it has on top. It's just pushing with 1/3 of the weight for a given Poisson ratio. Most rocks, they have a Poisson ratio which is 0.25 or even smaller. Many carbonates have a Poisson ratio which is in the order of 0.1, 0.15. We do have some other types of rocks and sediments that have a larger Poisson ratio. For example, salt rocks, or very soft mud rocks or shales can have an effective Poisson ratio which is close to 0.5, and therefore those type of formations are going to push with almost all their weight laterally, and the effective horizontal stress is going to get closer to the effective vertical stress. And I say here I involve something very specific that I call it an effective Poisson ratio, because many of these materials are not really linear elastic. But sometimes this simplification of assuming the material is linear elastic and defining an effective Poisson ratio, it can be useful in practice. And this is what we have done in this case. Okay, so let me build an example over here, and I'll be right back into this page. But now with this equation we can tell what horizontal stress is at a given site, and as long as we know the effective vertical stress, if we know the total vertical stress, if we know the pore pressure, then we know the effective vertical stress. If we know the Poisson ratio for this one-dimensional strain condition, then we can calculate what is that effective horizontal stress. And this kind of model has been pretty useful in some cases to predict what is horizontal stress in many cases. And here let me say a paper that tells you what I just said, and is using this uniaxial-strain model in order to predict horizontal stress in many places in offshore in the North Sea. And here I have the paper, and let's just look at some results. Here you have all the theory that we have already seen, and let's just go to the results. You can see that the predictions in green from this model that we have seen get very close what is predicted with actual leak-off tests, which are used to measure the minimum horizontal stress. So whether if it is a coincidence that this elastic model works well in the field or not, that's something that we're going to discuss more in detail throughout this course. Personally, I think that it's halfway between a coincidence and a physical model. I think that some of these models, as we saw before, we can calculate this sort of effective Poisson ratio, even though some materials are not linear elastic, that allow us to utilize this equation in order to predict horizontal stress. But we're going to see also some other properties of the materials that can help us to determine a little bit better this horizontal stress, also taking into account more complex processes that happen in the subsurface. All right, so in this simple example, I have assumed that the horizontal stresses are all zero, and also the shear strains are zero. And this is how I arrived to this simple equation. All right, what about now if we extend this model to include tectonic strains? So this is what is called a one-dimensional. It's not a one-dimensional strain anymore, but it will be a one-dimensional because it's just done in one dimension mechanical earth model with tectonic strains. And in this case, I'm going to relax two of my assumptions, and now epsilon 3.3 is going to be different than zero, and the horizontal strains also are going to be different than zero. The shear strains, I will still keep them equal to zero. And if this is the case, then what I have to do is I have to follow the same procedure that I did for these equations, but now if these two are not zero, I'm going to obtain equations of sigma 1,1 and sigma 2,2, which are going to be a function of sigma 3,3 through epsilon 3,3, but also as a function of epsilon 1,1 and epsilon 2,2. So it takes about one page of derivations to do that. We're not going to go through that here, but I'm just going to show the result. The result is right here. So you do all of this math, and at the end of the day, this is what you find. The sigma 1,1 is a function of sigma 3,3, epsilon 2,2, and epsilon 1,1. All right, so let me copy this and paste it into my notes. And we'll continue with the discussion. All right, so this is the equation for sigma 1,1, for sigma 2,2, and the one missing here will be sigma 3,3. Sigma 3,3 is just going to be equal to the vertical stress S33 minus the pore pressure at a given site, and we already know how to calculate this vertical stress. All right, so now that I have these two terms, additional two terms, notice that this part is the additional stress which is caused by the tectonic strains epsilon 11 and epsilon 22. So in our model, these are just horizontal strains, but in the subsurface conditions, usually these strains are caused by tectonic events, either extending or compressing the earth crust. And notice too that this term is the one that we had before. It's just the lateral stress coefficient, or lateral effective stress coefficient, also called K0. All right, so let's see if my model now has already been built over here. And I have one example. Apparently it is. And here what I'm doing is I just coded these equations that we just saw into a model in which the strains they increase with depth. And for example, if I have a Poisson ratio equal to 0, then that means that solids are not going to expand laterally as you put stress on them. And because of that, the effective lateral stress is 0. And because that's 0, is going to fall in the line of the pore pressure. So that effective lateral stress is 0. Effective vertical stress is not 0. As long as I add a little bit of Poisson ratio, then my effective horizontal stresses increase, and so do the total horizontal stresses. Let's put it in typical 0.25. And now I can see my two horizontal stresses, which are in the same place, and they are about 1/3 of the effective vertical stress. And now if I add these tectonic strains, for example in direction, let's go in direction 2 first, I add a little bit of tectonic strain, then S22 and sigma 22, it increases, and it increases more than sigma 11. It makes sense because I'm applying a tectonic strain in direction 1. Notice that sigma 11 also increased, but not as much as sigma 22. And if I have a lot of tectonic activity or horizontal compression, then my horizontal stresses may even go above the vertical stress. And if I have also an additional strain in perpendicular direction, horizontal, then that's going to increase too. And if that one is also so large that it goes over the vertical stress, then I might go into what is called a reverse faulting regime. Remember that always these equations are applied to effective stresses. And if I have my pore pressure to change, then that's also going to affect the value of the total stresses, because let me come back here to the base case without tectonic strains. For a Poisson ratio of 0.25, I'm going to come back to the condition in which the horizontal stress is about 1/3 of the effective vertical stress. So if I keep on increasing the pore pressure, then that rule is going to still hold. All right, so if you want to play with this link, it's right over here under equation 3.34. Okay, so now we have a model that can be used to predict tectonic strains as a function of depth. There is one more thing that we have to clarify in here, and this is that whenever we apply this model, we just derived it to one point at a given depth. But you can also apply this model to a stack of sediments with different Young modulus. So in that case, for example, if I had a stack or a sequence of layers, all of them with different Young modulus, for example, E1 on Poisson ratio 1, E2 on Poisson ratio 2, and so on, all different from each other, I could also apply this model that I have in here, but then I would have to define what is a tectonic strain, and what is usually done is to assume that that tectonic strain or deformation, it is the same in all layers. And for some intervals, this is quite reasonable, as long as they are not very, very long. So, for example, let's say in this case that this is a strain. Let's respect our coordinate system that we had before. Let's see what it was. It was 1, 2, 3. So this case, epsilon 1, 1 is different than 0, and epsilon 2, 2, let's say, is equal to 0 for a coordinate system which looks like this. As a result, what I would expect from applying the equation that I have on top, then I would have a profile of horizontal stress sigma 1, 1, which is going to depend on the stiffness of the layer. And the larger the stiffness, the larger is going to be the stress. Why? Because the tectonic strain in this case is uniform for all this stack. So let's imagine that epsilon 1 is larger than epsilon, I'm sorry, that Young modulus 1 is larger than the Young modulus of 2, then I would expect to have something like this. And as I change in my layers stiffness, then also the corresponding stress is going to change. This is going to be a function of the Poisson ratio as well, but usually when you have a large tectonic strain, the tectonic strain is going to overcome the effect of the Poisson ratio. And that stiffness is going to be very important as well. And from this equation, what we can also notice is that we have combined Young modulus and Poisson ratio into a ratio that is called the plane strain Young modulus. And this is also another type of modulus, which is not Young modulus, and it's not the constraint modulus, which is very useful too, because it characterizes the stiffness of a solid for this given type of deformation, which in this case is called plane strain. So this is the plane strain modulus. And you can notice that these tectonic stresses are proportional to that plane strain modulus. All right. So lastly, how do you obtain these moduli from the field? Well, we'll see this in a different video lecture, but our objective would be to obtain this data from the field and then to apply it with this model in order to apply or to calculate horizontal stresses at a given site.